an overview of what we did in class today. This is on the 27th. It's 17, of course. 04, 27, 8, 9. Yeah, I think so, right? Okay. We started, and then we ended up the preceding class with this. Now, we went into a lot of details, and I'm going to give a kind of an overview of what we found, and then we'll look through the details, okay? So we didn't do this overview in class, and in hindsight, I kind of wish I had, but, okay. So we have this differential equation that we saw in the preceding class, and we did the Laplace transform on both sides, and the Laplace transform being a completely linear operator, it acts just like any linear operator, and that's already been commented on. And then we solve the equation that we get out of this. The equation that we get out of this is going to involve just the Laplace transform of y, okay? So the Laplace transform of y turns out to be this mess. Okay. So how are we going to inverse transform all this? You're not going to find any of these expressions in a table of Laplace transforms. You're going to have to manipulate. Okay, well, to manipulate this, we see an s squared plus pi squared, which reminds me of an s squared plus omega squared, and hopefully reminds you of that. Of course, you haven't looked at as many tables as I have over the years, and you're kind of new to it. So you might have to do a little bit of work before you get to this point. Hopefully you've already done that. But, and we're not sure what we're going to do with this, but the one thing we are sure of is we want to split this and this. So what we do is we just do a partial fraction. So we're going to say that this is of the form AS plus B over s squared plus pi squared plus cs plus d over s squared plus 2s plus 4. And we're going to apply partial fractions, that's what we're doing here, to determine what the values of a, b, c, and d are. And those values are a little messy because you got pi's in there, you don't have just plain old friendly numbers, okay? Pi's not that unfriendly, but it makes the expressions look a little bit intimidating. Just follow your wits, it's not bad. Okay, then this expression, whatever a, b, c, and d come out to, this expression is going to be a times s over s squared plus pi squared. Then it's going to be just b times 1 over s squared plus pi squared. Now, if we think about it for a minute, if we've done the integrals, familiar with the way this works out, and we probably aren't quite at this stage, but we will recognize this as the Laplace transform of the cosine of pi t. And we'll recognize this as a multiple of the Laplace transform of the function sine of pi t. And that's kind of good because we're going to have to be combining multiples of sine pi t and cosine pi t in order to solve the non-homogeneous equation. Okay? So we're going to get that out of here. Right here we're going to have our solution to the non-homogeneous equation. Sort of. But there's a little bit more because, of course, then we've got this thing, and I want to change colors here, okay? And yeah, I can write this as c times s over s squared plus 2s plus 4. Clearly I can do that, I just want to make sure I wanted to. Plus d times 1 over s squared plus 2s plus 4. Now since this 1 over s squared plus 2s plus 4 doesn't appear in any table, and neither does s over s squared plus 2s plus 4 or anything like that. you don't have any quadratics in your denominators on the table. You have to develop them as we're going to do, okay? Now, the way we deal with this is we complete the square on this denominator, and then it becomes more tractable. So we complete the square, okay? So I'm going to do that. I'm going to say, okay, let's see, s squared plus 2s plus 4 equals what? Well, on s squared plus 2s, s squared plus 2s plus 1 is a perfect square. It's s plus 1 quantity squared. So if I have an s squared and some multiple of s, it turns out that all I have to do is take half of the coefficient of the s and square it and add it, and now I've got a perfect square. Now you're going to have to, if you don't understand this, at this stage you should have encountered it many times in pre-calculus, in calculus, in multivariable calculus. We use it in almost every course up to this point. So hopefully you've encountered it, but if you haven't, you're going to have to review it. Okay, well, we can't just replace s squared plus 2s with s squared plus 2s plus 1, can we? But we can replace it with s squared plus 2s plus 1 minus 1. So I'm going to kind of put parentheses around the s squared plus 2s, and I'm going to put parentheses around this, and these are clearly equal. And then s squared plus 2s plus 1, well, that's s plus 1 quantity squared. And then we have minus 1, and then we have a plus 4, and we can dispense with the parentheses. We see that this is just s plus 1 quantity squared plus 3. Any quadratic you have, you can complete the square. Now you don't want to if you can factor it, because if you can factor it, then you can use partial fractions to simplify it. Okay? Yeah, just kind of checking the time. I don't want to digress to that, but I'll just say if this was s squared plus 2s plus, I was going to say plus 3, we'll say s squared plus 2s minus 3, it would factor into s plus 3 and s minus 1. And then you would have 1 over s plus 3 times s minus 1, and you could do partial fractions on that and break that into 2 fractions. If the quadratic in the denominator doesn't factor, you can't do that. And then you can proceed with partial fractions. And you can, of course, always proceed with partial fractions, whether it factors or not. And it will more or less work out. Okay. So, if we use partial fractions, we can then write all this, and I'll come back to my white color, as a times s over s squared plus pi squared plus b times 1 over s squared plus pi squared plus c times s over s plus 1 quantity squared plus 3 plus d times 1 over s plus 1 quantity squared plus 3. Now we'll go on from there, but this is progress. Now the other thing you're not going to see, though, is you're not going to see an s here and an s plus 1 squared here. You can see a 1 and an s plus 1 squared plus 3 here. This is just going to turn out to be a sign, but you're also going to have an exponential function in e to the negative t, it turns out, in this case. And it's a good thing that you have it, because if you do the solution to the homogeneous equation, you're going to get e to the negative t's, and you're going to get sines and cosines of the square root of 3t, and that's exactly what's going to come out of this mess.